morning, everyone. It's my honor to be here to present you our latest work on the effects of brain science on fatigue and wear behaviors of nickel-titanium shape memory alloy. I am Hao Yi from the Wuhan University, and I need to thank our PhD student, Dr. Pan Liu, and my supervisor, Professor Qingping Sun, from the Hong Kong University of Science and Technology. Okay. Before telling you our research work, I want to introduce our university, where we are. Okay. So here is China, and in the middle of China is Hubei province, and Wuhan city is here. Okay. Here is Wuhan city. And our university is in the middle of Wuhan. And this is our university. And our school and department is right here, near the East Lake. You're welcome to come here and visit. Okay. So today's topic includes 4 parts. First, I give you our research background. Thanks to the committee, I have 30 minutes to present our work. So to make our story more complete, I want to share with you our our works in these recent years. And then I will show you our research objectives and results. Finally, I give you our conclusions and future work. Hope we can have collaborations in the future. Okay. I think all of you are experts in this area, so we don't need to say much about the applications here and the background here, and background here for the materials. But I want to mention some latest applications nowadays. First is the limb lengthening device, developed by Ellipse Technologies, based in here, in San Diego. Okay. The other application is the Boeing 787. They use nickel titanium to build some actuators here, or in the engine cover, to change its shape and to maximize the fuel efficiency and more stable precision. Okay. And last year, I went to Japan to visit NIMS, their National Institute of Material Science. One of the professor, Mr. Sawaguchi, he built a company, and he's now selling a big or huge devices, huge parts or huge structures to build building, to prevent the building from multiple large earthquakes. These structures, as a damper, were made by iron-based shape memory alloy. And some shape memory alloy-based actuators to protect monuments can be found in Italy. And of course, some special devices for surgeries. Why they use nickel titanium or the shape memory alloy for all these applications? Because these materials has 2 special properties. One is superelasticity, and the other is shape memory. Okay. Since my focus, all the materials I used are shape memory, are superelastic materials, so I will focus on this property. So why we call it super? Because it has large, non-linear recoverable strength. Could be 7%, which is much higher than the conventional alloys and metals. Okay. But 2 things we need to focus. The first one is, during the loading-unloading cycle, 2 heat sources were involved. The first one is latent heat. It will release during the forward transformation, and absorption will happen during reverse transformation. The second heat source is hysteresis heat. Another important thing is that the stress during the phase transformation, the transformation stress is highly temperature dependent. Okay, it's a very complicated process. But with the experiment, we can see that. Okay, under different temperature, okay, their stress strain curves are different, and this is based on the Clausius-Clapeyron relation. Okay, so with these properties, people find out that with different strain rate, okay, with different strain rate, or in different ambient conditions, okay, the temperature hysteresis, the temperature history, and the stress strain curves varies a lot. Okay, this is because with different strain rate, the temperature, the specimen's temperature under this loading-unloading cycle are different. Since the stress is temperature dependent, so the stress will be affected. So in 2013, we've done a set of tests under different ambient conditions by using different air velocity and with different strain rate. We find out the hysteresis heat, which is the area surrounded by the stress strain loop. And this hysteresis, it can represent materials' energy dissipation ability, varies non-monotonically with the strain rate. And we find out in the different ambient condition, the peak happens at different strain rate. Okay? This is not good for us to predict its hysteresis. But when we normalize the time axis, or the x-axis, by this non-dimensional time scale, Tt over Th, where Tt is the loading period, and Th is the convection time, we saw that all the curves overlaps with each other. Okay, what this means? This means the control parameter of the hysteresis or the energy dissipation, D, is this non-dimensional time scale. So we have these two conclusions. The first one is damping capacity, which is the energy dissipation here, non-monotonically changes with this non-dimensional time scale, Tt over Th. And the peak we have at a critical Tt over Th. In this case, it's about 1. Okay. So this is for one cycle, loading and unloading. How about the side, and then we find out for the copper, aluminum, nickel single crystal shimmer alloy, they have the similar results. But this time we record the surface temperature. We find out the temperature varies. Oh, then we know the reason for these stress strain curves variation is the temperature. So the temperature affects the stress strain curves. Okay, but this is one way. This is one way affection. This is one way affection, but not. This is not thermomechanical coupling. So what is thermomechanical coupling? So we do multiple cyclic loading. Of course, some other research, some other groups have already done excellent works, okay, such as Professor Miyazaki and Professor Momi. Okay, they've done some experimental work and simulation work. Okay, but here are two problems here. The first problem is cyclic plasticity. As we all see here, large residue strain after several cyclic test. This cyclic plasticity is mixed with thermal effect, so that the pure heat effect cannot be clearly investigated. So we want to remove the cyclic plasticity before we investigate the thermal effect. So we built our own system by using MTS universal testing machine and thermocouple. Of course, nowadays we use infrared camera. Okay. So before test, we have calibrated the ambient by lumped system analysis, which is built by Cotter in 1997. And we do the training. As we said before, as I told you before, we don't want cyclic plasticity involved. So we do this training process. This training process ensures in our formal tests, the stress strain curves will no longer have cyclic plasticity. Okay? So the two objectives of this training process is, first, remove the mixed cyclic plasticity so that the material has repeatable stress strain curve. And second, in the later formal test, we can investigate the pure heat effect. So, the thermomechanical coupling. What is that? Okay. As I told, during the cyclic loading, two heat sources, the latent heat and hysteresis heat, will release an absorption. Release and absorption of these two heat sources will happen. Okay? This may cause temperature increase and drop. And this temperature variation will lead stress strain variation. At the same time, the stress strain variation changes the area surrounded by the curve itself. And this area is what we call hysteresis heat, one of the important heat sources. So the heat source the heat source changes when the cyclic loading going on. Okay? When the heat source changes, it will in turn affect the temperature variation. Okay, so the mechanical response will affect the thermal response. At the same time, the thermal response will affect the mechanical response. So they are coupled with each other via the Clausius Colombian relation. So which make it a very complicated process. Okay? But this is a very good scientific problem. So we want to find out how the temperature affect this, how this thermomechanical coupling process going on. Okay? And we find out during this process, two important time scales were involved. The first one is transformation time, which characterizes the heat release or the heat absorption time of the latent heat and hysteresis. Another time scale is the lumped convection time, which characterizes the ambient condition. Okay, so these two time scales have opposite effect for the temperature of the specimen. So they compete with each other. So what's the competition results? Okay, this is what we need to find out. Here I showed three typical experimental results. We can see that under very low frequency cyclic loading, the temperature variation is not that significant. Okay, the temperature variation amplitude is less than 10 degrees Celsius, and they looks almost the same for each cycle. Of course, for the stress strain curves too. They are very close to the isothermal case. But when we increase the loading frequency, okay, when we increase the temperature, first, the mean temperature will drop from a higher level to a lower level. Okay, and the temperature oscillation will become much more significant, to about 20 degrees Celsius. And as the mean temperature decreases, the stress-strain curves drift down. When we further increase the loading frequency, okay, it has opposite phenomenon. The mean temperature will increase. Meanwhile, the stress-strain curves will shift up. Okay, they are correlated, but how? We build our own model. And we find that with these analytical results, we find that the temperature variation during the cyclic loading can be represented as the superposition of the steady-state mean temperature, which changes monotonically with the loading frequency, and the transient state temperature change, plus the temperature oscillation caused by latent heat and hysteresis heat. Okay. So with this temperature variation prediction, we can predict the stress level during cyclic loading condition. And this is very important for engineering applications. But for engineering application, this prediction may work for 300 cycles, 500 cycles. Okay. How about 50,000 cycles? Or how about 5,000 cycles? Or 50,000 cycles? Or 10 million cycles? As we all know, material will go to fatigue. Okay, so this comes to our research objectives. How about we go further from the cyclic loading to fatigue? Okay, one of the most disadvantages of nickel titanium sheet metal alloy is that we cannot control its fatigue. Okay, and we cannot predict the fatigue lives, okay, only by test, but we cannot monitor it. Okay, we cannot say, oh well, after 10 cycles or after 10,000 cycles, it will break down. No, we cannot do that. So there are two objectives here for the fatigue test. One is, can we increase its cycle, the fatigue cycle? Second is, how do we monitor the fatigue process? Thanks to our Professor Sun's former PhD student, Dr. Aslan, he has done excellent work on controlling grain size of the sheet metal alloy. Okay, what's the usage? We can see that from his work, when the grain size decreases, the stress-strain curves change significantly, and the temperature variation also changes. So, from his work, we can see the grain size modification will cause two effects. First one is thermomechanical coupling effects will become weaker. Okay, maybe not good for scientific work, but it's good for engineering application. The second one is it will bring significant increase in fracture toughness. So will these two effects increase materials fatigue resistance? So this is my first objective. Will grain size modification increase fatigue life? Okay. And then the second objective is how to predict materials fatigue life and how to trace the materials fatigue process. Okay. And the second and the third research objective is for wear test. Okay, for wear. In MEMS, this wear means nano-wear tests. Okay, because nowadays many of these materials were used in MEMS system and it's small-scale devices. Okay, so we need to find out its wear behavior. Okay, so will the grain size modification affect the material's wear resistance? This is our objective. So we've done this with tests. So here I'll show you our latest experimental results. Okay. For the fatigue test, we use this dog bone-shaped shear memory alloy specimen, and we load it. Okay, we do tensile fatigue loads. Okay. And we put acoustic emission sensor here. Okay. Why we put it here? As I said before, we want to trace. The fatigue process. And luckily, I've been in Einstein Paris Tech in during 2014 to 2015, under Dr. He and Professor Moni's group. And they have many knowledge on the energy process, on the energy approach for test the materials fatigue process. So this gives me a hint. How about use energy approach to trace the fatigue process? So I use acoustic emission sensor to trace the accumulated acoustic emission energy. Okay, and here are our 3 typical stress strain curves of our 3 different grain size specimens. Okay, we manufacture them based on Asla's work. Okay, so we do the fatigue tests with under 2 different stress levels. Okay. One is 450 megapascal, the other is 300 megapascal. We've done these tests, and we find that during in the intermediate fatigue test, where the fatigue life is about 10,000 cycles, there's no such significant effects on grain size. Okay. However, in low cycle fatigue tests, we can see the 10 nanometer grain size specimen has significantly increased in fatigue lives compared with the other 2 specimens. Okay. So why this happened? Okay. So why this? I will show you later. The other thing is how to trace the fatigue process. Okay. Remember, we use acoustic emission sensor, and by recording the accumulated acoustic energy, we can see that we can separate the fatigue process easily by using different slope. Okay? And this different slope means different crack propagation speed. Okay? So we can separate the fatigue process to about 3 sub-processes. One is slow propagation, the other is fast propagation, and final fraction, which are 3 typical steps for fatigue fraction. Okay? And it also works for large grain specimen. Okay? So we can see this accumulated acoustic emission energy is highly correlated with the crack propagation speed. So we find a way to trace the fatigue process so that with this curve, we can predict the fatigue lives of a certain nickel titanium shear memory alloy applications. Okay. So again, for the fatigue life, why they are different? We observe the final fracture surface by SEM. We find that for the crack propagation region, they have different morphologies. Okay? For the large grain size specimen, we see some micro voids. However, for small grain size specimen, we can only see some micro This is typical. This is a typical metal fracture surface morphology, but this is not. Okay, but we can find some similar morphologies for dual phase steel. So we're thinking, when the grain size decrease, for large grain, the fatigue may be caused by the crack nucleation, or the extrusion and the intrusion from PSB or twin martensite. Okay, this was observed from others. But for small grain nickel titanium, since the phase transformation or slip bands were banned, so we think some possible new possible mechanisms for crack nucleation retardation by grain boundary sliding, rotation, or grain boundary diffusion happened for small grain nickel titanium JMML. But these are our thinking. We need some evidence. To prove we are correct. Okay, so we're now seeking collaborations. And with collaborations, we hope we can prove our guess, our thinking is correct. Okay. And then I'll show you our experimental results on the wear test. We've done the wear test by using a high-strong TI 950 nano indentation machine. And first, we calibrate our sample by testing its hardness, because we know hardness is highly related to the material's wear behavior. And we find out, by indentation tests, we find out the hardness of the test specimen is significantly increased with decreasing grain size. Okay, with decreasing grain size. And when the grain size decreases, the hardness increases, and this is good for wear resistance. But as I said before, when grain size decreases, the phase transition will become harder. So that, and based on others' work, this is not good for wear resistance. So these two opposite effects will compete with each other. So what's these competition results? Okay, we've done set of tests under different force level. Okay, first, under 100 micronewton, the surface morphology under different passes numbers are shown here. Okay, and these are the surface morphologies under 300 micronewton from 1 pass to 100 pass. And these are the surface morphologies under 500 micronewton. Okay. After analysis, we see that under 100 micronewton, 10 nanometer grain size specimen has best wear resistance behavior. Okay. However, the 80 nanometer grain size specimen performs worse. But when we increase the normal force from 100 micronewton to 300 micronewton and to 500 micronewton, the 80 nanometer grain size specimen performs the best. This is because when we increase the normal force, the phase transformation will be involved. And this phase transformation will increase the contact area, makes the contact stress becomes less. And this is good for wear resistance. So we can conclude that first, the grain refinement will bring significant increase. in materials fatigue life under low cycle fatigue, which makes a nickel titanium shimmer alloy as a high fatigue resistance applications. Okay. The other conclusion is the accumulated acoustic emission can be a useful tool to trace the fatigue process, okay, based on the energy approach. Okay. The third conclusion is different morphologies of fractured surfaces of different grain size specimen means something different, means the different mechanism. However, further investigation needs to be done to prove our thinking is correct. Okay. And the fourth conclusion is for wear test. We saw that the hardness will be the dominant factor of wear resistance under light loads. However, the phase transition still has its dominant position in the long use of heavy loads. This is because phase transition will be involved. Okay. So in the future, we need to do some further investigation on the fraction mechanisms behind two different grain size specimens. And now we are doing some research on functional gradient nickel titanium shimmer alloy and self-healing nickel titanium based composite. We hope some interested researchers or groups, we can collaborate, have collaboration, okay, to make the research better. Okay. So here is my presentation. Thank you for your listening. And comments and questions are welcome. Thank you.